Welcome back to the Simscope. In today's video, we are diving into one of the most important building blocks in the power electronics, the three-phase full-wave rectifier. Whether you are in powering industry drives, like DC motors or high power converter, this rectifier is everywhere. But how exactly does it behave under the different load condition? Let's see today, okay? So in a single phase rectifier, the output DC is bumpy and has a high ripple, and it isn't always suitable for a large scale application. So how do we get the DC waves smoother? That's where the three-phase rectifier comes in. But here's the catch. The type of load you connect, whether purely resistive or resistive reactive load, the output waveform significantly changes, especially the current. So mm, I have three-phase rectifier model here, and I would like to explain you first the model architecture. I have three-phase voltage source connected in star and ground configuration with the phase-to-phase voltage or 400 volt VRMS at the frequency of 50 Hz. Then this three-phase is given to the rectifier circuit. The rectifier circuit have 6 number of diodes, 2 diodes connected in series and three pairs of diodes connected in parallel. I have a diode number 1, number 3, diode number 5, then diode number 2, diode number 4, and diode number 6. This is connected to the load, and the phase A voltage is connected between the diode 1 and diode 6. Phase B voltage or phase B is connected to diode 3 and diode 4. Phase C is connected to diode 5 and diode 2. Okay, I'm using a three-phase power instantaneous power block to find the active power and reactive power at the source side. Then I'm using a demux, and from the VABC, and I give it to three-phase RMS block to find the VRMS. The RMS block has the following parameters, and I can find a VRMS in this display block. Then similarly, I'm finding IRMS, and you get a three-phase power here. Then at the load side, I have current measurement block connected in series to the load, and I'm giving it to the main block again with the a fundamental frequency of 50, and I get IDC. This is a average DC current. Then I have one voltage measurement block that will measure the voltage across the load, and this is also given to the mean because we are finding the average DC voltage, right? And I'm getting IDC and VDC. When I multiply IDC and VDC, I get the output DC power. So what are we doing here? We have a three-phase source. Then we are giving three-phase source to the three pairs of diode, and the diode will switch with switching with the rectifier switching scheme. It gets the three-phase sinusoidal AC power gets rectified or converted from AC to DC. That's what we are doing. Now I have one more voltage measurement block that will measure the voltage across the diode number 1, and I am finding VRMS divided by VDC, and I'm searching for the form factor. Okay, I have used a couple of go-to blocks to collect the data, and I'm giving it to the final scope, and I have my uh, purely resistive load of 100 ohms. Let's simulate this and see the results. You can see that the input is a AC power, right? And we have a DC power output. So dividing the PDC divided by PAC, I am getting a rectification efficiency. So for the purely resistive load of with the purely resistive circuit of a resistance 100 ohms, I'm getting efficiency 90%, and usually compared to the half-wave rectifiers, three-phase rectifiers have very high efficiency and low ripple factor, ripple in the waveform. So what I'm getting a VRMS of 230, then I'm getting IRMS of 4.3 amps, then PAC is 3193 watt, and rated power is minus 37. This is because of purely resistive load, and my form factor is 0.42. For the ideal case, the form factor should be 100%, so we are getting almost 428%. That's great. Then at the DC side, I am getting a IDC of, firstly VDC of 538.6 DC voltage, and I'm getting IDC of 5.38. You can divide 538 divided by, we have a lot of 100 ohms, right? Yeah, so 538 divided by 100, we get 5.38, and our DC power output is 2901 watt, 2901 watt, and you can see that there's not much of a losses considering the consumption from the resistive load, and we are getting a efficiency of rectification efficiency of 90.8. That's great. Let's see the waveform. Okay, I do not make this one for now, and let's off this one, and okay, what is the orange one? Okay, let's say that phase A, phase B. The yellow one is a phase A voltage, phase B voltage, blue is a phase B, and C is a phase C voltage. And this is the voltage across the load. This is a DC output voltage. You can see that it is a pulsating waveform, and it is a DC waveform, and we are getting a peak DC waveform of 563, 64, and average of 530 something, right? 538, yes, average. Now, if I make it small and show you how does the diode works. We have a pair of a diode, and we are connecting the each phase to in the middle of a diode pairs. So let's say that this is a phase A, and phase A, if we start from here, from here to here, from here to here at the middle, the yellow is a phase A, blue is phase B, and orange is phase C. Voltage waveforms. This is a AC voltage waveform. This is a input VIN. And from here to here, the phase A is, if you compare, from here to here, the phase A is highest, yellow is highest, and the lowest is negative here. So blue is phase B, so lowest is negative, and highest is phase A. So in the model, what happens? The highs will be conducting forward biased, and when it returns, and other diodes will be reverse biased, and when it returns, the lowest will be forward biased, and two of these diodes will be conducting and carrying the current. So from here to here, the phase A is highest, therefore phase A is highest, and the diode 1 is forward biased, and it will conduct, and it will pass through the load and return back. While returning, we have the lowest blue, which is phase B. We have connected the phase B to diode 4, therefore returning diode will be diode 4 and go back to the source. So this is how the current, how the diodes switch. In the another half, from here to here, again diode 1 will conduct because it is highest phase A, and lowest is phase C. So that means returning will be, the current will return from diode 2 because diode 2 is forward biased. And then next, from here to here, you can see that blue, which is phase B, is highest, and orange is lowest. So since phase B is highest, the diode 3 will be conducting, and while returning, phase C is lowest, so diode 2 will be conducting. And you can, if we continue this, then you can see that there is a pattern where each diode will conduct for 120 degree, or 120 degree. Then how are we getting the how are we getting our voltage the voltage is multiplied. This is because VDC is equals to 3 root 3 divided by pi Vm. That's why we are getting our VDC out here. Then we have a current which is the blue line, which is around 4 amps. Oh, okay, it's a 5.38 amps, and it is constant. It remains constant because uh, it is a resistive. We have a resistive load, and it does not change. Then now we have a diode 1. You can see that since the diode 1 is conducting from here to here, while conducting it does not, and its voltage across the diode 1 is 0, and once it is stopped conducting, then you can see that the voltage across the diode 1 is increasing, and till here it is not conducting. Again it is conducting, or forward bias, then not conducting. This is the resistive load waveform. Okay, once more, this is a 3-phase AC waveform. Then we have a 3-phase, then we have a DC average VDC here. Then we have DC current, and then we have voltage across the diode. Now let's change the load to motor, DC motor. This is a DC machine, and I would like to put it into a field type permanent magnet, which requires a mechanical input is torque. And for torque, I'm saying that my initial value is 0 and final value will be 1, and at the step time of 0.5. And I have a scope that will give me the parameters, motor parameters. Let's simulate and see how the outputs are. Okay, I have also made a video on a single phase half wave rectifier and single phase full wave rectifier. You can go to my channel and watch if you are interested. Now, firstly, this is the output from the motor scope. What do we have here? We have a yellow one, it's a speed, motor speed. Then blue is a DC machine armature current. Okay, then orange one or red one is field current, and green is a DC machine electrical torque. Okay, this is a torque. So let's see what happens with the speed. At start, the speed is 0, and it gradually increases as the torque accelerates. Yep. So the torque is accelerating the rotor, and while it is accelerating, the speed is gradually increasing. and it settles at the steady speed around 300 radian per second. So rotor speed is around 300 radian per second. Then we have a blue. This is an armature current, and it is very high at the start because this is an inrush current, because the back EMF from here to here is 0. Initially the back EMF is 0, and the peak is around 700 amps, 700 or 750 amps. Then it decays as the motor picks up the speed. And it decays and develop the back EMF. Since it is developing the back EMF, the armature current decays. Then what about the field excitation current is, or the field current is constant at a 0. That's expected because field winding is supplied separately with the DC, so it does not change dynamically. It should be 0. And finally the green is a electrical torque. It is very high at the startup because we have a high armature current. Since we have a high armature current, the torque is very high at the first, and its peak is around 1350 Newton meter, and then decreases as the motor accelerates. The motor speeds up, the torque decreases, and again it approaches the load torque at a steady state. So it will be somewhere here. It is at a steady speed. Okay, that is the dynamic behavior of a motor. And let's see the waveform here. You can now see that the load current has changed. Earlier in a purely resistive load, we had a blue line here at a constant, and since we are using a motor which draws a very high current at initial, so the current in the rectifier circuit also changes and act like a inductive load circuit. So that is the difference between the resistive and purely inductive load. Okay, for a resistive load, the output voltage has 6 pulses per AC cycle, and the current flows the same pulsating shape like shown here. And for a RL load, the current becomes almost like a continuous. There is a difference in the current waveform, right? So the key takeaway: three-phase full wave rectifier naturally gives the smoother DC than compared to the single phase, and adding an inductance in the load, it improves even more. So that's why most high power DC systems rely on this configuration. So that's all If you found this breakdown useful, don't forget to like, share and subscribe to the Simscope for more deep dives into the power electronics and other motor controls, or if you need custom video files, check the link in the description. See you in the next video. Thank you for watching. Thank you.